right, Dr.
And
Langary.
we are spending money on the workshop. So sooner you can get me some money.
So sit where you can read size 16 font.
Yeah, let me turn the light off.
I almost was able to go to
You all
18.
manage with this, or?
Well, if the
Or no?
light's off, then
Too much?
let me go to the white slide. You tell me if it's clear enough for you guys. And well, I mean with
That's
the,
good
with the
with the
light
light.
on.
Okay, actually, the light
Well,
is.
wait a minute. There's a secret set of lights here
Oh.
that nobody knows about.
Okay, yeah. Excellent, okay,
All
good.
right.
Just for
So-
you guys.
Thank
Okay.
you.
I wouldn't divulge that secret for anybody else. We got everybody, right?
Yes, sir. So if you had a chance to get your water and whatnot, then I'll
Yeah, thank
start
you.
as soon as Dr. Morgan's all set.
Got his cookie.
Okay.
Okay, good afternoon. Thanks everybody for being here. And I'll get started right away talking about the mechanical design and optimization of a standardized CubeSat for my thesis defense. So let's outline what I'd like to talk about right now. And I'll start with background and research objectives. I'll go to the multidisciplinary optimization problem that I created and sensitivity analysis and a Pareto Front. I'll go into the mechanical design and the prototyping process, covering the design for manufacturability, finite element analysis, and then move on to results, lessons, and suggestions for future work, including the machining results, the MDO results, and my overall contributions. And then we'll have some time for questions and extras if you'd like to explore that. So I provided this table here just so we can cover some of the terms that are abbreviated in the slides. Power, batteries, solar panels are all abbreviated. X sub n refers to design variables, where X is the design vector and X star is the optimal design. P sub n refers to parameters that are put into the MDO problem, and G of X and P, J of X and P are the constraint function and objective functions, and they're functions of the design variables and the parameters. A little background on MDO for CubeSats specifically. There's a small number of papers you can actually find on this combination of topics. They include a rather extensive study by University of Michigan folks on maximizing the power generated and the data transmitted to Earth by a 3U CubeSat. And they're taking an existing satellite design and optimizing the configuration to achieve those goals. And for an uncertainty-based MDO, there's one that is maximizing capability for a lunar mission specifically, and once again, it's using an existing payload, and the propulsion system is already decided on for this optimization. There's one covering the feasibility of a novel thruster design, and it's optimizing efficiency of delta V maneuvers and actually changing the trajectory of a satellite to alter its orbit and things like that. And then my study is going into optimizing cost effectiveness of the satellite and leaving open variability for different types of missions, not going off of one type of design existing. Also, I'd like to note that I wanted to take a systems approach instead of just covering mechanical simulations, because this figure kind of sums up what I found when I was reading background. It comes from a study called the First 100 CubeSats, and it's showing that 8% of the failed CubeSat missions are due to mechanical failure. So I don't want to dwell too much on extensive mechanical simulations. Okay, background on CubeSat prototypes. First, I'd like to cover what's shown in Figure 1 here, and it's that we have an envelope of 119 millimeters of width, and most existing satellites do not take this full envelope. They're only limiting themselves to 100 millimeters, so I wanted to be able to take advantage of that. Then we have different styles that I came across. Image 2 comes from CubeSatKit.com, and this is a flight-proven unit. and it's made from sheet metal, which is something I want to stay away from because of the large investment cost to make a one-off prototype using sheet metal and meet tolerances. This would be rather expensive. We have a prototype from Thesis, and I downloaded this CAD model, and it turned out to be one of my favorite benchmarks, but it does have some intricate machining, which causes it to be rather expensive. And Figure 5 shows that this CAD model was shared with me by NanoRacks with an unknown designer, and it does take up the full envelope available, but it's not accounting for manufacturing whatsoever once you open up the CAD design and find the radii and whatnot.
I'm sorry, what happens if, when you said it doesn't account for?
So this model, as shown, could not be manufactured at all, because if you extruded it or if you cut it or some combination, you couldn't achieve all of the corners shown in here internally, and some features you could find a way to do it, but overall it's
That's
not
the
a good
discussion we had, right, so that's the discussion we had earlier today. Okay.
So the objectives of my research are to maximize mission effectiveness and minimize the mass of the critical functions. So I'm treating the CubeSat like a vehicle, a pickup truck that needs to carry a payload, and I want to minimize the mass, the resources taken by those critical functions, leaving the most remaining resources for the payload so it can do its job. I want to optimize for cost effectiveness, so include commercial off-the-shelf components where we have known information on the data sheets and known costs and as much of that information as possible. Maintain flexibility to re-optimize for different missions, and take advantage of continuously growing data that's available. So here in this image, I have a 2U configuration of my design, and the optimizer is able to design, if we allow it, a larger satellite with this configuration. And I went to make a prototype that's fed by the optimizer and is designed for manufacturability. So the output of my research is something that does not need to be redesigned in order to actually be made. So I'll cover the multidisciplinary optimization, but I think most of you have seen it once or twice already. I have a design vector including 6 design variables, 3 of which are considered fully discrete, and 3 of which are considered, for my purpose, they're allowed to be continuous. And the objective function is to minimize the mass, and then secondarily, an objective function of minimizing cost is introduced to gather a trade-off. Then there are 3 major constraints. The first one is power must be met, power demand must be met by the solar panels and the batteries in combination. The structure bending stiffness must be sufficient, and that's based off of a benchmark. And the propellant is sufficient to achieve the delta V we need, which we're not going to actually change our trajectory. We're using delta V as a measure of attitude control force. So an example of the constraint is this power constraint shown in this equation, which is basically saying we're summing up all the currents of all the components that are drawing power, finding their power, their duty cycle, and multiplying that by the length of the mission in days. And then we're saying that that needs to be less than or equal to the power that's generated by our power sources.
So if you compare your design objectives, right, and constraints with the prior work, like you mentioned, work at the University of Michigan, right?
Mm-hmm.
Could you compare what their objectives were versus what you're using as objectives?
Yeah, so they're strongly oriented towards capturing the most sun using their solar panels, and so their objective was maximize the power, maximize the transmitted data, and so they're dealing with timing, and they also take the impacts of their angles of their solar panel configuration. That impacts their flight as well. So their objective is maximizing this stuff. My objective is to minimize cost, but my constraint is to meet the power demand. So their objective is kind of like my constraint. And I pulled power demand examples from other cubesat. Whenever I found out how much power is taken by an attitude determination system, then that's what I used as my estimated power demand and those kind of things. So this is my n-squared diagram. It's showing the flow of all the modules that are computing the objective function. We start with the design vector, and then it feeds information about the design variables and the parameters into all other modules. And it's been adjusted to make minimal feedback loops, but there's one feedback loop, and that's where the propulsion module takes the chosen thruster and decides how much power is going to be used by that thruster. And then it feeds that into the battery and power module, which is going to accommodate the solar panels and batteries to meet that. And then finally you have a mass of all that equipment, and that mass gets updated and goes back to propulsion so that our delta V can be met, and the propulsion might adjust the amount of propellant to still achieve the delta V with a new mass of satellite. And after mass is calculated, then the cost is somewhat decoupled, and it's all calculated at the end. So for my optimization approach, I created a two-stage approach, and that means I'm using the genetic algorithm, which is a heuristic method, to calculate the first three variables. Now actually it calculates all 6 variables, and it's just doing its best to minimize the objective function. And then we take the result of the GA, and then we feed the first 3 variables, which are discrete, into the gradient function, and we treat those as fixed parameters. And then we allow the SQP to do work and maximize the efficiency of the last 3 variables, which are number of solar panels, number of batteries, and structure rail width, treating those as continuous. And this can guarantee that we have a local minimum, because the gradient is going to be 0. So in this example, the GA was able to form a design at 902 grams, and then SQP was able to to reduce that to 886. And the overall process is fairly repeatable. At least 1 out of every 2 times that I run using the same parameters, it will give the same result. And oftentimes you'll know if it got stuck and made a bad decision based on the genetic algorithm, just ending up with a result that's at least 10% or 20% higher. This is describing our function of minimizing the objective function such that the constraints are less than or equal to 0, and the design variables fall in between the lower bounds and upper bounds. So after finding an optimal design point, I need to check the sensitivity of the objective function to those variables. So we look at mass sensitivity, and we find that out of the continuous variables, the mass is most sensitive to the structure rail thickness. And to do a logic check here, we look at the overall CubeSat mass. We find that the structure is taking up a mass that is equal to both the batteries and the panels combined, and so it should have a greater impact. And then when we look at cost sensitivity, we find that the solar panels have the greatest impact. And once again, checking our overall cost comes majorly from the solar panels, and the cost of a solar panel is about $1,500 in this scenario, and the cost of the battery is only set to be $10. So we should expect to see a greater impact from solar panels. I also did a parameter sensitivity study where I adjusted parameters of the mission, such as the duration or the power that's able to be generated by one solar panel. And I can share that at the end if you'd like to know about it. So we want to develop a Pareto Front that shows us options for designs that have varying cost and varying mass, but all of which are optimal. And the Pareto Front that I was able to generate from this two-stage system is okay, but could be improved. The new objective function in order to create this front is right here, J star. It's a combination, it's a weighted sum of the cost and the mass, taking lambda as lambda increments from 0 to 1 in n number of iterations. And we basically have the results converge to these data points, give or take a few data points each time that I run it. And you'll find that there may be a false Pareto point like this one here, where it got stuck because the heuristic optimizer chose a design that just wasn't in the right ballpark, and then the gradient-based function still minimized locally, but it couldn't jump to the correct spot. So what I did in this picture is try to capture, going from right to left, what is the major design change that was chosen, what major variable was changed that impacted it and caused it to move upwards. And so that's what these comments are here. It is hard to capture all that information in one graph, so I summarized it a lot. For example, this point here is where the batteries had been moved from the lower bound to the upper bound. It means all of these designs had batteries at the lower bound, and then it finally decided that the trade-off is worth it, so that we take on a lot more mass of using more batteries, but reduce the cost of using the solar panels. So next was mechanical design and prototyping. I began this process with the benchmark because I love benchmarks, and I took this ISIS panel here, and the first thing I did was send it out for a machining quote to find out how long would this take to machine, and that came out to be 10 hours. And my goal here was to reduce the cost, maintain the function, and make a design that's fed by the optimizer. I'll talk about the third bullet point next, but in order to reduce the cost, I was raising the minimum tool radius required to cut the panel. So these very fine radii in here, I eliminated those, increased the tool diameter by double, and then you can cut faster, and you can also have reduced tool wear when you're machining the parts. And then secondly, I reduced the thickness of the raw stock needed to make the part. So if you're just considering making this part and starting with a raw material or a raw plate, I reduced these bosses so that your thickness is reduced by 50% at least, and then those bosses carried some functionality that had to be replaced. For this, it was for mating to the other components, and I had to add in holes in order for my part to still be functional. So when I got a quote for this part, it was reduced all the way to 3 hours, and it didn't include the holes. So in order to add those holes, it would be conservative to say that that new quote would be increased to 4 hours. So this slide's talking about how is it that the design takes results from the optimizer. Well, the optimizer considers the whole frame to be consisted of one cross-section beam. So all these external rails are considered to be of the same cross-section shown here, and the constraint is that the bending stiffness of my beam must be equal to or stronger than the bending stiffness of the benchmark. So the benchmark it's made of two different angles. It has these cross sections, and the third image is my cross section that has a greater area moment of inertia than both of those, and those area moments of inertia are shown here. So in the A-axis, that's the principal axis, bending axis of greatest strength, and A prime is 90 degrees of that, and it's the lowest strength. And so this baseline for the constraint is greater than both of these. And then, since the bending stiffness comes from the area moment of inertia and the modulus of elasticity, if the optimizer chooses steel instead of aluminum, then it's allowed to reduce L if it wants to save weight, and it would still maintain that constraint. And then the area of moment of inertia for section A is shown here. So the next step was to take my model of a 1U and subject it to some finite element analysis. The analysis that I did here in this slide is to do 1,000 Gs of gravity downwards. And image 2 is showing how it would deform in an exaggerated manner under 1,000 Gs. And image 3 is showing the regions of the material that have a factor of safety less than 15. When that factor of safety for iso clipping is set to 3, then you don't see any red regions. So then I took the analysis that I did, and I wanted to do a convergence study. So I started with a coarse mesh, such as the one in figure 4, and then I gradually refined that mesh to a finer and finer mesh and reran the study iteratively. And then I was checking each time what is the minimum factor of safety for all regions of the material. So I want to see that the result converges, and it's not as nice as I wanted. The convergence actually goes from right to left when you get finer. So it's not as beautiful as I would want, and if I want to fully trust the FEA, then I would consult with somebody that's more experienced to say, is this a behavior that's good enough? But in general, we're staying between 2.5 and 3.5 factor of safety, so it's not extreme jumps, and so I'm happy to see that. If I could confirm that the FEA is trustworthy and sufficient to say that the design is strong enough, then we could move away from we could create designs that are less similar to the benchmark in geometry and just use the FEA to stand by rather than staying similar to a benchmark to claim that we're safe. So as I continued with prototyping, the goals were to meet the tolerances, improve the speed, and find any weaknesses in the process that would cause it not to be manufacturable by the method I expect. So starting with the 8 hours from the quote, this is hours to build 2 panels. We started with 8 hours, and then my first trial on building 2 panels yielded about 6 hours to build them. And then what I did was time-cutting measures such as building a fixture that improves, that takes away time for lining things up, and building a CNC code that's cutting 2 panels at once instead of just 1 panel at once. And I was able to reduce the time all the way from to 2 hours and 21 minutes. So the final check for the prototype is to meet tolerances and fit it where it's supposed to fit. So image 1 is showing the cubesat fitting into the P-pod deployer check fixture. So the deployer comes from NanoRacks, and they're the official company that's delivering these to space. And so if it fits in their check fixture, it's a go. And it did, in fact, fit in the check fixture. And also, I was measuring each part that came off of my CNC to find out if it's meeting the tolerances that I just decided. And so we're not 100% meeting the tolerances, but you have to keep in mind that I'm changing the process each time to speed it up. So the best tolerance here would likely be a repeatable tolerance once the process is set in stone. And my solid red line refers to a tolerance, if exceeded, could cause interference between 2 mating parts. And my dashed line here is a tolerance that would not cause any interference if it's violated, but it's not serving the design purpose so well. Then finally, I designed and built a modular component called the fixed panel, and you can see that the fixed panel can simply be an inert panel, or it can carry a solar panel, or it can carry a deployable antenna that I also designed, but I did not prototype. So, for conclusions, what I've drawn from the research is that a heuristic method is capable of optimizing a CubeSat and is enhanced by gradient-based functions to do work on the continuous variables. I found that more commercial off-the-shelf subsystem data would be required to make a design that's fully, truly usable, and that the manufacturing costs can be lowered by at least 50% from some existing designs. I don't have a guarantee that I benchmarked the lowest cost design, but I benchmarked a functional design and was able to reduce the time to build it. And this is based off of a piece-by-piece evaluation, where not 100% of the pieces are evaluated. So this is what I have in recommendations for future work. One is to validate the X-star design with a full prototype. This means building the model with all the subsystems, checking the power draw and checking the propellant required, and then going back to our numbers inside the model and updating them if they need to be changed to be fully representative of the truth. Then that model will be fully useful. So then adding heuristic data to the Pareto Front would give us a more full Pareto Front, more options, and possibly better options. So if, for example, I added magnet torquers, which is a magnetic device for attitude control, then the optimizer might choose that altogether instead of all propellant and eliminate those needs for the propellant and the tanks. So this would be useful. Adding multiple timescales to the optimization would make it more representative of the truth as well, because I have a constraint that says over the whole course of the mission the power demand is met, but what about during that half an hour in the shade where it's not getting any power from the solar panels? In my model I made a minimum number of batteries for that reason, but it's not it could be improved by adding multiple timescales. So adding any details that impact performance in general, anything that I didn't account for that is standard in a CubeSat, such as heating requirements. Some satellites have heaters that protect some elements from failing to operate. So maybe the thruster, maybe one out of my 3 thrusters can't operate in too cold, and then you would need an extra power draw. So that kind of relevant data needs to be added. And then a fancy thing to do would be write a CNC generating code. So the optimizer would actually use the CAD design and be able to manipulate the CAD design, and then output a CNC code that tells you how long does it take to manufacture and how much material is removed. Then we could really fully integrate the machining with the optimizer. So I have references to sites, and I have time for questions, and these topics that I kind of mentioned but didn't fully elaborate on. So now's the time for questions. Oh, and that's my reminder to give the handout so you can go through other slides if you wanted to.
So going back to that comparison with the other studies that have been done, let's say definition of right? So they focused more on optimizing the operational parameters like power delivery and data transmission rate, those sorts of things. And you focused more on not the operational aspects, but more like the capital cost aspects of it, right? Basically, what is the mass and right, what is the cost to build this and so forth, right? So it's kind of like the perspective is very different, right?
Absolutely.
The perspective is different. So they assumed that cost is no object and.
Every
mass-
study I've seen assume that cost is no object.
Right.
It's a bit